Hey everyone, Videos Gunner here. As you know, the derivative of a function at a point is equal to the slope of the line tangent to the function at that point. If we extrapolate this over an interval, we can determine where the function is increasing based on the sign of said slope, whether or not the function is above said tangent, all the wonderful types of discontinuities, and hold on. All of this is cool, but how do we get from here to this beautiful graph over there? Now, our goal here is sketching the graph, which means we need to account for literally every single point everywhere, and finding the exact values is kind of a waste of our time, since we're concerned with the shape of the graph in particular. This means that we need to stop thinking about the points and start thinking about the intervals where stuff stays the same and the in-between states where stuff changes. Because we've stopped worrying about exact values, it's more useful to display all the information that we derive from the algebra stuff on the right on a number line first. 3 number lines, really. Each derivative gets it once, so that we can determine the graph's shape with more accuracy than a light switch. This will let us condense all our future information onto a single axis, a triple parallel differential graph, if you will. This guy has everything we need: relationship with the axes, interval properties, and stuff about the points of interest. And hold on, that doesn't look right, okay? Don't worry though, we only care about the shape and features of our graph, and we can stretch and shrink things as needed later. It's easier to visualize stuff with this wonky scale that would make Mercator and Gall jealous. Well, not really. They have us beat on the front of trying to project a curved surface into a space 1 dimension lower so that all the math regarding its features works out nicely, by a few hundred years. Anyhow, let's look at what we do have in terms of, numbers and symbols and all that. We only got our functions and of course the x-axis. Luckily we can determine where they are relative to each other by finding the roots. We do need to distinguish, however, between roots where the graph crosses the axis from ones where it just touches the axis and then goes back whence it came. Algebraically, odd power factors result in alternate roots, while even power factors result in non-alternate roots. We'll denote these as single and double dot, respectively. The zeros of the derivatives also have effects on the graph. Alternate roots of the first derivative manifest as either local maximum or local minimum points, since they represent when it changes direction. The roots of the second derivative represent inflection points, where the graph switches from below the tangent line to above it, or the other way around. Asymptotes behave similarly to roots, because they're based on the denominator rather than the numerator factors. The odd powers alternate and the even powers do not, and they're likewise instead by a single and double bars. If a factor is both in the numerator and the denominator, though, then it cancels everywhere except for when it's 0, creating a point discontinuity or hole. These are labeled as circles and do literally nothing useful except converts the points above and below into degenerates like them. I bet you didn't even realize I was being homophobic there. Anyway, we now have all our points of interest, so we can move on to describing the intervals. We only need to sample 1 point to determine where one section is positive and negative, and since we have all the points where the sign changes, we can extrapolate their status to the rest of the graph. The function sign tells you its sign, and also, nobody likes you. The first derivative sign tells you if the function is increasing or decreasing, while the second derivative tells you if the function is above or below the tangent line. Alright, let's compile this whole process into an actual example. Alright, take this function, which is secretly a reference to my last video. We can use the basic derivative rules to find f prime and double prime. Factor the numerators to find zeros, factor the denominators to find asymptotes, sample x equals 0, and extrapolate the interval signage. Onto our graph. Divide it up, plant the zeros, asymptotes, and scribble the rest of the graph accordingly, and there we go. Only took me a whole year. But, I'd say it's worth it. I'd say it was worth it.